The new section is entitled Solving Separable Differential Equations. This is going to be the first section where we're actually solving a differential equation. But first, I want to review some very basic algebra. If you have 3x over 4 is equal to 7 over 13. It's very simple to solve this. Everything in the left numerator is being multiplied 3 times x. That makes 3 and x factors. The bottom is just 4. There's only one factor on the bottom. In fact, let me put a 5 down there. On the right side, the numerator has one factor, it's 7. The denominator has one factor, it is 13. How you solve this problem is you move the factors about. Now, I want x to stay right on the top where it is. So I move this factor 3, which is on the top. I move it to the bottom. The 5 on the bottom, I move to the top. The 4 on the bottom, I move to the top. X is 20 times 7 over 13 times 3. That's what x is. If you have 5x over 7 is equal to 22 over 17. Very, very simple problem to solve. Just move the factors. The 5 on the top goes on the bottom. The 7 on the bottom, it goes on the top. It looks like 154 over 85. That is what x equals. If you have a times b plus c over d plus e is f over g plus h. First thing I might say is recognize that bottom is one factor. With brackets around it, it's one factor. Because whatever in the brackets you think of as one factor. It's the rule. And the bottom over here, g plus h is one term. Sorry, one factor. And I already had the brackets, but just to make it clear, b plus h is just one factor. And I want to solve for a. Okay, so I'll move this factor to the bottom, and I'll move that factor to the top, and I have what a equals. I've been amused over the years at how teachers would solve this problem. How I would solve this problem is as follows. I will move this x to the top, because I want x in the numerator. I don't want the 5 there, so I move the 5 to the bottom, and the problem is done. You mean you can switch these? Of course you can. 10 over 2 is 5. And 10 over, and if I switch these two, I get this equation. And yes, 10 divided by 5 is 2. Of course it's got to work, because the product of these two numbers is supposed to equal the top. Well, if I switch the 2 and the 5, the product doesn't change. So yes, that product is still going to equal the top. If you have a problem like this, it's as easy to solve as can be. Just switch those. Or if you prefer, this is on the bottom, move it on the top. It is 7 times x, and move the 7 on the top to the bottom. You're going to use that a lot in separable differential equations, or in separating the differential equations. You have 2 plus 3x times dy plus y times dx. Now, before I go on, our goal is to get some function of x times dx equals to some function of y times dy. Now, if that function of y is 1 over y, well then this will be dy over y. That is, we can have y's in the denominator. We want the x's on one side, the y's on the other side, and dx and dy in the numerators. Oh, this is equal to 0. So now I could move this term to the other side. So 2 plus 3x times dy is negative y times dx. Okay. Dx is on top, dy is on the top. I want all the x's on the dx side. That is, this side is x's. And the other side, where dy is, I just want y's. Oh, look, that factor. So let me just write this down again. And then we'll look. I only want y's here, and I only want x's here. Ooh, look, that's a factor of x. Let me move it to the x side. It's in the top, and move it to the bottom. Oh, that's a factor of y. Now you can just say you can just say y. That is, you can just move the y if you like and leave the minus sign. But I'll move the minus sign as well. So we have negative dy over y is equal to dx over 2 plus 3x. We separated the differential equations. Now I can integrate both sides. I'll integrate the left side. Notice I factored up the minus sign. I'll integrate the right side. The left side is negative that integral. Well, the integral of dy over y is ln of y. And on the right side, if I call that u, if I say u is 2 plus 3x, well then du would be 3dx. Oh shucks, I only have dx on the top. But the 3 you can put in, a number, a constant, you can put in. You can't put an x in. You can't put an x squared in. But you can put a constant in, as long as you multiply in front by the reciprocal. After all, 1/3 times 3 is 1. So I have the 1/3 in front, and I'm gonna be honest. Students are not honest. That is 3dx. Oh, I can call that du. Students just say, oh, I'm gonna call that du. Unless you wrote it down here, you're probably wrong. And that is u. It says 2 plus 3x is u. So I have negative ln of y is 1/3 times ln of u plus a constant. This 1/3 I can bring up as the power. It's ln of u to the third plus c. Now here is a trick. Well, I don't know if I want to call it a trick, but here is something that you're going to use a lot in differential equations. C is just a constant, the same as ln of c. That is, instead of calling that c, I can call it ln of c. It's a different c. This is c star. It's a different c. 2, for example, is ln of e squared. That is, if that's c, then my c star will be e squared. 7 is ln of e to the 7. So I guess I know what that c star was. C to the c. It is some constant. Why is that correct? If you can bring down the c and you multiply by ln of e. If you think about it hard enough, you'll realize, oh, but ln of e is 1. C times 1, you got it, is C. Now, the reason we want to do that is now I can use another rule. Ln of A plus ln of B is ln of A times B. This is ln of A plus ln of B. This is nothing more than ln of B times A. Cu to the 1/3. So now, let's look at what we have. Negative ln of y is equal to this. Ln of c times u to the 3rd. But what is u? 2 plus 3x. Okay, now if I multiply both sides by negative 1, that is, if I change both the signs of both sides, I make this positive and I make that negative. So then ln of y equals, I can bring this up as the power. Now basically we have c times 2 plus 3x to the 3rd. I have to raise the whole thing to the negative 1. So I get c to the negative 1, which is just c, times 2 plus 3x to the 3rd to the negative 1. But you multiply those powers and you get negative the 3rd. C times 2 plus 3, 2 plus 3x, excuse me, to the negative 1/3 power. Okay, one last rule. Lots of rules. If ln of one thing is equal to ln of another thing, then those two things are equal. That is, y is equal, oops, what happened to the ln? That's just a typo. Y is c times 2 plus 3x to the negative 3rd, or if you prefer, y is c over 2 plus 3x to the 1/3. Now, one last thing I want to do, I want to prove this last statement is true, this little theorem. This is the ln of x graph. It passes the horizontal line test. To get this value, to get, say, 7, you have to take ln of just that number. Whatever that number is, it is. Whatever that number is, whether it's 7.5 or 9 or 0.12. To get ln, you have to take ln of this number right here. Ln of that number equals that number. And ln of only this number. You can't take ln of two quantities and end up right here or right here. You have to take ln of that number right there to get that value. It's called a one-to-one function. We solved our first differential equation. And remember that this equation right here was the same as this equation. That is, it was the same as dy over y, negative dy over y is equal to dx over 2 plus 3x. And I'm going to move things around. So basically, I want to show you how you would check this. Just going to move things around. I want to get dy dx. Well, dy stays where it is. Dx is in the top. I put it in the bottom on the other side. The y on the bottom, I put on the top on the other side. The 2 plus the 3x stays where it is. And the negative Doesn't matter when you cross it to the other side if you put it on the top or the bottom. But basically, this is the equation that we just solved for. This original equation, unless I made a silly mistake, and let me just verify that I didn't. These two equations are exactly the same. And I claim that when you take the derivative of this function, you will get that answer. And you can check it. Take the derivative of this and take the derivative of this, and you will get that. And if you don't, you can check your error or find your error, or I'm wrong. dy dx is equal to cosine of 3x. The first thing I want is I want the dy's and the dx's in the numerator. This is in the denominator. I cross the equal sign and I put it in the numerator. And then I say, oh good, that was a function of x right by the dx. So everything's fine. dy is equal to cosine of 3x dx. Now you can integrate both sides. The integral of the left side is y. We'll do it this time, plus the constant. So constant 1. Now, if I let u equal 3x, well then du is 3 dx. So this part is going to be cosine of u. That's going to be cosine of u. But dx, I know dx is not du, and lots of students say, oh, whenever I see dx, I put du. No. Whenever you, in this problem, whenever you see 3 dx, you put du. Well, you can sneak in the 3 as long as you bring in front of 1/3. There's the 1/3. There's the 1/3, the integral sign. That part is cosine of u, and this part is du. So I have y plus a constant is 1/3 times this integral. And the integral of cosine of u is sine of u. Why? Because the derivative of sine of u is cosine of u. Plus a constant. We're integrating on the left side and we're integrating on the right side. So each side is going to get a constant. But if you bring this plus c1 over to the other side, well then, that c2 minus c1, I'll just call it big C. It's just a constant. Y is 1/3 the sine of u plus some constant. And if you take the derivative of this, the left side is dy dx. Oops, one little typo. U is just what it says it is, 3x. Sorry about that. That u is 3x. Derivative the right side, the constant stays, times the derivative of sine of 3x. The derivative of sine of any angle is cosine of that same angle times the derivative angle, which is 3, plus the derivative of c is 0. These cancel out as 1, and 1 times cosine of 3x is cosine of 3x. Exactly what we started with. So there's your check. Just separate them. Everything works out nicely. You have that dy dx is x plus 2 cubed. The first goal is to get the dx's and the dy's on different sides and in the numerator. Of course, I'm going to erase this one real quickly. There's always a 1 on top. I can always move this to the bottom. And let's even further make believe that was a y. Okay, that is, if the original problem was this, I can fairly easily get the x's and y's on one side. Remember, there's a 1 there. 1 dy over dx is y plus 3 cubed. I can just cross off the dy and put it in the bottom. Now this side just has x's and that side just has y's. But we don't want that. I mean, if you got this, that's okay. Then take the reciprocal. Then take the reciprocal. And everything is fine now. You want the dx's and dy's in the numerator and x's and y's on one side. Good, just move this to the top and we're done. Because that already is a function of x. So now we integrate both sides. And the constant of integration we'll just put on one side. Since this integral is just y, and I could just write y equals, or I could write y plus c equals, I'm just going to write y equals. That is, I'm going to put the constant on the other side. If I let u be x plus 2, then du is 1 dx. That is du. That is, I have the integral of, u cubed, because that is u, this is u cubed, and that is du. So y is equal to u to the 4th plus c. Y is whatever u is to the 4th plus c. And I'm not going to try to remember what u is. I'm going to read it. Oh, u is, x plus 2. There's your answer. And of course I have one sloppy mistake. I'm sorry about that. The integral of u cubed is u to the 4 over 4. So I should have u to the 4 divided by 4. Y is x plus 2 to the 4th over 4 plus c. And I caught that mistake because when I took the derivative, the 4 was staying. When I brought this 4 down, it stayed. So now that 4 here is going to kill off that 4 in the bottom. And the power 4 becomes 3. That is, I'll have x plus 2 cubed if I take the derivative of this. Try some more. How you learn. Just keep doing these. dy plus y plus 4 squared dx is equal to the number 0. First thing I'll do is I'll bring this to the other side. So I have 1 dy is negative y plus 4 dx. Since that factor is a y, I put it on the bottom. And that minus sign you can put on either side of the equation. Now, if I would have let u be y plus 4, then du was just dy. That I can call du. This is says I can call, those two horizontal lines have many meanings. One of which is I can call dy du. Now this is u because it said this is u. Sorry. It says this is u. So this will become u squared. If I bring it to the top, it comes u to the negative 2. And this is equal to, so I'm integrating both sides. This is equal to the integral of dx, and I'll put the minus in front. Now this integral is u to the negative 1 divided by negative 1. I added 1 to the power, and this time I divided by that power. On the other side, I get negative x. Well, I can quickly change the sign of both sides. So what that last line now says is u to the negative 1. Dividing by 1, the rule for that is don't do it. Yeah, don't bother. If anything divided by 1, you just get back, divided by 1, you just get back to anything, to 7. This is equal to x. That is 1 over u is x. That's 1 over u, 1 over y plus 4 is equal to x. Now that's acceptable, but it'd be nicer if I can say what y equals. Just remember that this x is over 1. I take the reciprocal of both sides, and I get this. And remember that dividing by 1 doesn't do anything. Just bring the 4 over now. Y is 1 over x minus 4. That would be your derivative. And you can take the derivative of that, and you would get back the correct answer. Now, what is the correct answer? What do you mean when you say get back the correct answer? Well, let's look at this equation. If I move this dx into the bottom, that's the correct answer. That is, the derivative should equal to this, negative y plus 4. This equation is exactly the same as that one. So let us actually check this. dy dx is negative y plus 4 squared, and I claim y is 1 over x minus 4. I've been known to be crazy. Let's see if this is one of the times. Y is equal to 1 over x minus 4. That is, it's x to the negative 1 minus 4. So dy dx is, bring down the power, it's negative 1 x to the negative 2 plus nothing, or minus nothing. Derivative of 4 is 0. So I get negative 1 over x squared. Okay? Which, by the way, is the same as negative 1 over x all squared. Now you may say, yeah, you're right. This does equal that. But the dy dx is supposed to equal that. Well, remember we said this was y, I mean, that's what I wrote there. If I solve for 1 over x, if I add 4 to both sides, that's 1 over x. That's 1 over x. Oh, so I have negative 1 over x squared. But 1 over x is y plus 4. Oh my, he's right. We got back the same answer. Okay? It's called magic, folks. E to the x times y times dy dx. This is supposed to be e to the negative 2y plus e to the negative 3 minus 2y. So immediately I want to move that dx over to the other side. But the other side is 2 terms. I know. They're separated by an addition sign. Not a word. Put it in brackets. Now it's 1 term times dx. e to the xy dy is equal to e to the negative 2y plus e to the negative 3x minus 2y all times dx. Now, not every differential equation is separable. And for example, so it's e to the 3x, sorry, left side, it's e to the x times y times dy. So that e to the x, I can move to the x side, I put it in the bottom. But you just can't take e to the negative 2y and put it in the bottom on the other side. Why? Because it's not a factor. The whole mess, unless you rewrite it, the whole mess is one factor. Now remember that you add exponents if the bases are the same. This, what, e to the negative 3x minus 2y is the same as e to the negative 3x times e to the negative 2y. Because when you add those exponents, you get negative 3x minus 2y. Exactly what we got. So, what happens is, so let's just write it down. E to the negative 2y plus e to the negative 3x times e to the minus 2y times dx. Now, I claim that I can factor what's inside those brackets. This is the separator of the terms, and on close inspection, I say, look at this, look, they both have a factor of e to the negative 2y. So I can factor it out. And then what I didn't underline is plus e underline in black. It's plus e to the negative 3x. And that gets multiplied by dx. And you're like, blank space plus e to the negative 3x? You need to be mathematically mature enough to know that there's a 1 there. So when you factor out e to the negative 2x, a 1 still survives. It's e to the negative 2y times what's in the brackets times dx. Bye-bye. I can move this. I can put it in the bottom as e to the negative 2y. But since it's negative, I'm going to put it on top as e to the 2y. Now this equation is separable. Well, we separated it. The original equation was separable, but now we separated it. We have e to the 2y times y is equal to 1 plus e to the negative 3x dx. And now, I left out the dy, sorry. And now we can integrate both sides. Which are going to be a pain in itself. So what is the integral of e to the 2y times y dy? Well, this is a problem that we do by parts. Now first let me recall something for you. We have e to a number times x dx. That is going to equal to e to the kx divided by k plus a constant. Example, e to the 7x dx. You can let u be 7x and du will be this, or you can just say it's e to the 7x divided by 7. There was 17, so e to the 17x, we will take e dx, if it was this integral, you get back e to the 17x over 17. So it was e to the integral e to the 12x dx, you get back e to the 12x over 12. Now, there's something called, a lot of books tend to call the tic-tac-toe method. tic-tac-toe method just goes like this. There are two things being multiplied, not including the dy. E to the 2y and y. If you can take the derivative of one of them enough times to get to 0 and integrate the other factor the same number of times, you can use the tic-tac-toe method. Now, the derivative of e to the 2y, well, it's e to the 2y, the derivative will be this, the derivative of that will be this, the derivative of that will be this. You're not getting to 0. In fact, it'll never go to 0. But if you take the derivative of y, you'll get 0. You have y, the derivative of y is 1, the derivative of 1 is 0, which is good. Now we integrate. Just like I wrote down the factor y first, I'm going to write down e to the 2y first. And the integral of that is e to the 2y over 2. And the integral of that is e to the 2y over 4. Here's why they call it tic-tac-toe. You multiply that with a plus, and then you subtract that, and if there's another line, you would add that product, and then subtract that product. So what we're getting is plus y times e to the 2y over 2. I just multiply those two, then minus, and now I multiply that diagonal. E to the 2y over 4, plus a constant. So the integral of the left side is y, this left side, is y e to the 2y over 2 minus e to the 2y over 4. And with respect to the constant of integration, I'll put it on the other side. And how I integrated was using this rule here. K was 2, so I kept dividing by 2. I divided by 2, then I divided the 2 by 2. If I did it again, I'd divide that 4 by 2, etc. Okay, now, next term, next integral. What is the integral of 1 plus e to the negative 3x dx? Well, it's the integral of 1 dx plus the integral of e to the negative 3x dx. The first integral is simple, it's 1, it's x. So the question is, what is that integral? If I call that u, then du will be negative 3 dx. So I have an integral, and I have e to the u dx. How do I write dx using du? Well, if you had a negative 3, then you can call it du. But then you have to bring out negative a third. So you get x minus a third times that integral. Because adding a negative is the same as taking away. Adding negative a third is the same as just taking away a third. And the integral of e to the u is e to the u. But u is negative 3x. Minus 1/3 e to the negative 3x. Plus your constant. Now, not always can you solve for y. Now, on the left side, between the 2 and the 4, 4 is the common multiple. And 2 times 2 is 4. So I multiply top and bottom by 2, excuse me. Now, I have 2y e to the 2y over 4 minus e to the 2y over 4 is equal to this mess. Now, what's common in each of these two terms on the left side, well, it's visual. It's e to the 2y over 4. It's e to the 2y over 4. And whenever you say everything's common in one of those terms, there's always a 1. So I can factor out what's common, and then I write down literally everything that I didn't circle. 2y, the 2, the y, the minus, and the 1. X minus the third e to the negative 3x plus 3. Now, no way do I see how you're going to solve for y here. And if you like to make it a little bit cleaner, I'll multiply both sides by 4. Since this is one term, when I multiply it by 4, that cancels. And since this is 3 terms, I multiply each of them by 4. And 4 times c is just another c. That's the best you can do there. It's implicit. The next one. Suppose you have dy over dx, and this is equal to 3y plus 4 over 5x minus 2, and it's all squared. You're like, oh my, the x's and the y's are both being squared. How can I separate it? Well, you're supposed to know that if you have a over b, and you raise it, the whole fraction, to any power, it's a to the n over b to the n. Just like when you're multiplying a product and raising it to the nth power. You can raise it to the nth power first. That is, this is 3y plus 4 squared, just y's, over 5x minus 2 squared, just x's. That sounds pretty simple then. The dy I'll keep where it is. The dx I'll move to the other side. The 3y plus 4 having y's, I'll put it here. And the 5x minus 2 squared, since it's on the x side, I'll leave it just where it is. So just go factor by factor. Do you want to move? No. Do you want to move? Yes. Do you want to move? Yes. Do you want to move 5x minus 2 squared? No. Now, so now we want to integrate both sides, and we really should rewrite it and put a negative 2 dy and a 5x minus 2 to the negative 2 dx. On the left side, if I let u be 3y plus 4, then du would be 3 dy. Okay, I'll put a 3 in, and I'll bring out a third. So there's the third in the front. That is u. It actually says that's u to the negative 2. And 3 dy is du. And on the right side, if I let u equal 5x minus 2, well then du would be 5 dx. So I put in a 5, and then that's du, but I have to bring out 1/5. That's u to the negative 2. And like I just said, 5 dx is du. Now adding or solving these integrals is straightforward. U to a negative 2 du, you add 1 to the exponent, you divide by that same number. On the other side, you have 1/5 times this integral, the same integral. You add 1 to the power, you divide by negative 1. You can cross off common factors. So now you have 1/3 times that. So since that has a negative exponent, I'll put it in the bottom. And you have 1/5 times that. Since it's in the numerator and has a negative exponent, I'll put it in the denominator. Plus c. 1 over 3 times u was over here, 3y plus 4. 1 over 5 times u. U was 5x minus 2. And this is equal to c. Now this plus c is just c. In this case, I can solve for y. I'll take reciprocals. But we have to be very, very careful. The reciprocal of a over b is b over a. Okay? But the reciprocal of a over b plus c over d is not the is not the reciprocal of a over b plus the reciprocal of c over d. For example, the reciprocal of a half plus a half. Well, a half plus a half is 1. The reciprocal of 1 is 1. So now, if you take the reciprocal of each fraction 1 by 1, the reciprocal of a half is 2, plus the reciprocal of a half is 2. You get 4, which is not correct. You have to take the reciprocal of 1/4 to get 4. A half plus a half is not a quarter. So why am I saying this? I'm saying this because when you want to take the reciprocal of the sum, you're in trouble. Now, of course, if you had 3x plus 5 over 7, there's the sum, but everything's over 7. The reciprocal is okay. Why? Because you can think of 3x plus 5 as one term, which makes it a factor. But if you wanted to take the reciprocal of 3x over 7 plus 5, first you have to get a common denominator. You'd have to multiply the 5 by 7 over 7. So here the top is 3x plus 35. 7 times 5, 35. Well, that becomes the bottom. And the bottom becomes the top. Okay, so enough for this review. Right now we have, bottom right, we have this fraction is equal to this fraction plus c. Well, this c has to have the same denominator as this fraction. That is, I'm going to multiply it by 5 times 5x minus 2 over 5 times 5x minus 2. So now, to the right of the equal sign, I have everything over some denominator, namely c times 5 times 5x minus 2. Now I can take reciprocals. Of course, I have 1 plus that. When I take the reciprocal of the left, I get this. When I take the reciprocal of the right side, I get 5 times 5x minus 2 over 1 plus, I'll say 5c times 5x minus 2. Now it's up to you whether or not you want to distribute that 3. Because I have every right to cross it out and put it on the bottom there. So now I'm going to take away 4 from both sides. So I have that 3y is 5 times 5x minus 2 over 3 times 1 plus 5c times 5x minus 2 minus 4. Now, if you want, you can put the same denominator now you divide by that 3. So y is going to be, so this is the current bottom before I divide by the 3. This is the current bottom. So I can cross off that 3 and put it down here. And of course 3 times 3 is 9. And the top is just what it is. 5 times 5x minus 2 minus, and I can multiply the 4 and the 3 to make 12. 12 times 1 plus 5c times 5x minus 2. And that is what y equals. A lot of algebra, but like always, doable. Another one. Sine of 2x dx minus 2y cosine 2y squared dy is 0. If you subtract two quantities and you get 0, the very next step is you should write down those two quantities that multiplied out to 0 and put two horizontal lines between them. If they had no difference, they must be equal. The difference between this and that is 0. There is no difference, which means they're the same. They're exactly the same. So now you can integrate both sides. Unless the angle is u or y or t or w or the Greek letter gamma or beta, just one letter, call the angle u. If u is 2x, well then du is 2dx. So I'm going to call that sine of u. But then I have dx. I have to write dx using u's. If I had a 2 being multiplied by the dx, I can call it du. Or you can put the 2 in. You can put the 2 in as long as you bring a half out in front. And now, times 2 dx is the same as times du. The right side. If I let u be 2y squared, well then du will be 4y dy. So that piece is going to be cosine of u. What's left over? Answer, 2y dy. Oh wait, if I multiplied it by 2, I'd have 4y dy. And then I can call it du. But I have to bring out a half. Okay. 1/2. The integral of sine of u is negative cosine of u. And u was 2x. Equals 1/2 times integral of cosine of u, which is sine of u. And u is 2y squared. Plus a constant. You can always see a half there if you like. I'm going to kill off a half everywhere. So I have negative cosine of 2x is sine of 2y squared. Now, you could interchange this, the angle, and the other side. You can interchange them. You can say 2y squared is equal to the sine of negative cosine of 2x. But you have to put an inverse there. If I divide both sides by 2, I'll get y squared is equal to the sine inverse of, I'm not going to have room, am I? You divide, let's try it again. You divide both sides by 2, you will get that y squared is the sine inverse of negative cosine of 2x divided by 2. So therefore, y must be plus or minus the square root of that mess. The sine inverse of negative cosine 2x all over 2. And that 2 is definitely under the square root sign. So now, let's do see one silly problem again. This time I wrote plus c, but I didn't carry it over. It's really 2y plus c. I interchange what's in the boxes. So let's scratch this. And it's very, very simple. With all these steps, it's very simple to make some kind of an error. So right now, top and the bottom, we have 2r squared plus c is the sine inverse of negative cosine of 2x. Taking away c from both sides, I get that. Dividing both sides by 2, I get that. Why don't we just leave it like that? Y squared equals that. Absolutely correct. It's very messy. Suppose you have that d capital T, T for temperature, and little t for time, is some constant times t minus 30. So we want to solve this. The first thing I would do is I'd bring the dt on top. T minus 30 is one factor, capital T, and I'll put that in the bottom. So I have dt over t minus 30 is k times dt. And integrate both sides. If I call this t minus 30u, then du will just be dt. That is, I have the integral of du over u, which is ln of u. U is t minus 30 equals integral of a constant times d little t is k little t plus a constant. E, there's a base e here. E to the other side is equal to what you take in ln of. E to the k t plus c is t minus 30. But right here, please, let us look at how forever and ever we're going to say e to that power. Now remember, this is long and tedious. You want to stop doing it. This equal sign is valid because in multiplication, if the bases are the same, you add the exponents. And kt plus c is certainly that. So now, remember, c was just a constant. Just like e to the c is just a constant. And I'll write the constant first. E to the kt plus c. We are forever and ever going to write it that way. So, copying this down at the top, we have e to the kt plus c, which is this. This is t minus 30. You add 30 to both sides, you are done. That's what t equals. Suppose you have dy dt plus 2y is y times t e to the t squared dt. Now, the thing I see here is I have three terms. On the left side, terms are separated by addition and subtraction symbols, just like on the right side, but there are no addition and subtraction symbols. I have three terms. Our goal was to get some function of x times dx plus the function of y times dy and equate them. That's three terms. That leads me to believe if it's if it's separable, I can put two of these terms together. Now, this term has no y's and t's other than with d's in front of it. I'm going to pass that to the other side. The y dt is, you know what, the only way this is going to work, I'm sorry. Oh, I understand better now. There is no dt there. Sorry. Now, if I pass the 2y over to the other side as negative 2y, and then I say I can factor out the y, so between these two terms, I factor out the y, so what's in blue remains. T e to the t squared minus 2. Okay, so I'll put this over here. So dy is equal to y t e to the t squared minus 2 times dt. And that y is on the bottom. And these two integrals are not very bad. Well, first, let's say the integrals. The integral of dy over y is just ln of y equals. Now this integral I can think of as two integrals. Integral of that dt minus the integral of 2 dt. Now, if I call this u, then du would be 2t dt. So this is e to the u, and the 2t dt, or that's du. But if you put a 2 in front, you have to put a half. If you put a 2 inside the integral, you have to bring a 2 in front. Minus the integral of 2 dt is 2t. Plus some constant. So you have ln of y is equal to 1/2 the integral of e to the u du is e to the u, where u was t squared, minus 2t plus c. Okay. Now remember that ln is a shorthand notation for log base e. E to that power should equal y. E to the 1/2 t squared minus 2t plus c should equal to y. Can we bring that c out from inside the power? E to the 1/2 t squared minus 2t plus c. Well, isn't that the same as e to the 1/2 t squared minus 2t times e to the c? Because you would then take this exponent and add c to it and say it's e to that sum, which is just what I have, but e to the c is just c, and I can put the c in front. I'll put the c in front, I'll get rid of it, and that is what y is equal to. Next couple of problems will be initial value problems. Suppose you have dy dx is equal to x squared minus 1 over y squared plus 1. So we can think of the x squared minus 1 as one term, which makes it a factor, and the y squared plus 1 is one term, and move the pieces. Well, I surely want to move the dx to the numerator. Okay, I just did. And the y's, I want it by the dy. And we're done. We separated it. Y squared plus 1 dy is equal to x squared minus 1 dx. And I lied. I also said that this was a initial value problem. Suppose that you're told that y of 0 is 2. Now remember, you take y of x's and you get back y's. Y of 0 is the same as f of 0. You take f of x's and you get back y's. That is, x is 0 and y is 2. The integral, you get y cubed over 3 plus y. The right side, you get x cubed over 3 minus x plus a constant. So we need to find the constant. When x is 0, y is 2. Okay? So x is 0, y is 2. 2 cubed over 3 plus 2 is equal to 0 cubed over 3 minus 0 plus c. The right-hand side is just c. So we have c is 8/3 plus 2, which is the same as 2 plus 8/3, which is the same as 2 and 8/3. Even though that's a mixed number, even though that's an improper fraction, we can still play our little game. 3 times 2 is 6, plus 8 is 14/3. So now the answer to this differential equation is y cubed over 3 plus y is x cubed over 3 minus x plus 14/3. And no, you do not have to have x's on one side of the equal sign and y's on the other side. But nonetheless, there's your answer. Let's do one more, folks. dy dx is, well, let's do it this way. Negative 2y equals 1, and y of 3 is 5. So that's a y value, and that's an x value. Now we're only supposed to have two terms. So I'll bring the negative 2y over. I have one term on the left, and if I put brackets around what's on the right side, it's one term. Okay, now we move things around. Dx has to go on the top, the y's have to go on the bottom. So dy over 1 plus 2y is dx. Now, I just want to comment on one thing, please. Just like after I brought the 2y over and I had 1 plus 2y, I said I can think of it as one term. You can surely think of this as one term, but then you won't be able to get the dx's on one side and the dy's on the other side. Okay, it's going to be a disaster doing that. Actually, you could, but it'll be a disaster. You'd have to get common denominators by multiplying by dx, and then factor out a dx on the bottom, put it on the top, and could have left the one there. So then you have dy minus 2y dx equals 1 dx. And then you'd have to combine the dx's. You have 2y dx plus 1 dx, which factoring out the dx, you get this. Same thing we got. Oh, and then you'd have to move this to the bottom. Alright, now let us integrate this first one. I'll do it here on the side. If I let the bottom be u, then du will be 2 dy. So the bottom is u, not a problem. And a lot of students say, oh, if only I had a du here, I'd be in business. So they put a du. That's what I mean by not being honest. This piece, every piece has to be accounted for. That piece is u. This piece is, oh, I don't know. But I do know if I had a 2 there, then yes, it's du. But if you put in a 2, you have to bring out a half. So now I get 1/2 ln of u. So the left side is 1/2 ln of u, where u is 1 plus 2y. And the right side, some integrating. The integral of x, the integral dx is x plus c. Okay. Get rid of my side work here. I'm going to multiply both sides by 2 to kill off the half. So ln of 1 plus 2y equals, now multiply that side by 2. 2x plus 2c. But that's just another c. Say e to this, which I write that way, is equal to 1 plus 2y. Take away 1. The right side is just 2y if I take away 1. Dividing both sides by 2, that tells me what y is. That tells me what y is. But I have to find out what c is, because it's initial value condition, initial value problem. When x is 3, y is supposed to be 5. So I have c, e, to the 2 times 3, that's 6, take away 1, over 2, this is supposed to equal y. So 2 times 5 is 10, that means that numerator is 10. Well then that's 9. Sorry, it's 11, it's 11. 11 minus 1 is 10, so c, e to the 6 is 11. And now We just move around factors that we don't want where they're located. I want C alone, so I bring this to the bottom. So C is 11 over e to the 6. So recopying this down, I have y is equal to C, which is that value, times e to the 2x minus 1 all over 2. Now you can keep that answer just one more moment, and we'll be done with this problem in this section. We have that y is 11 over e to the 6 times e to the 2x minus 1 over 2. Now, if I take each term and I multiply it by e to the 6, that's allowed, and no more denominators in my numerator. I have 11 e to the 2x minus 1 times e to the 6 is e to the 6. The bottom is 2 e to the 6. And there is your answer. That completes the section on separating differential equations.